start my recording. So first of all, 6:03 in the news. I'm not going to talk about this a ton because I didn't read all of the details of the current infrastructure plan in the US. But one thing I wanted to point out, and the staff and I talk about this a lot, it comes up in staff meetings all the time. The things that you learn in 033, you can really take to a lot of places in the world, and not just in computer systems, but thinking about like infrastructure in cities and things like that is very much a systems problem, right? If if roads don't exist and aren't built where, it is hard to get things from one place to another, things like that. So I would just encourage you, as you see news about about infrastructure, think of it in the context of 033. It's pretty illuminating. It can help make sense of some things. And so as we, if we find more interesting infrastructure things, I'll certainly bring them up. All right, so what are we going to talk about today? Today is the last lecture in the networking section of 033. And you've seen a bunch of different networking protocols so far, right? You've seen Ethernet in recitation. We've been through a lot about routing, right? Link state, distance vector, BGP, RON, all of those issues. We've talked about transport. We talked about queues. You've seen DC, TCP, all of these things. So what we're going to do today is we're going to move up to the top layer of this layered model. We're going to talk specifically about some systems that interact with the application layer. And so, there are so many different applications, right? It's kind of impossible to imagine that we would somehow talk about like every application on the internet in a single lecture. And indeed, we're not going to. What I'm going to talk to you about today is in some ways like a single issue. How do we deliver content on the internet, right? Like after all, what is a network for but to help us get content from one place to another? And what I'm going to focus on in this lecture is how the actual architecture of the internet affects this problem. So we'll look at a few different approaches to doing this. And this lecture is also going to serve as a nice bridge into the next part of 033 when we start to talk about failures in large distributed systems. So you will see me a couple of times during this lecture point out problems that exist in these systems and tell you that we're going to solve them, in a couple weeks. And so I'm not doing that to, to sort of bring stress or leave you with a lot of unanswered questions. I just want to start to expose you to the types of things we're going to be solving starting next week. All right. So content delivery. How do we do this, right? In some ways, there's a sense in which the internet was almost designed for this. So file transfer was one of the original applications on the internet, along with a lot of other things, remote jobs, remote login, all of those sorts of things. But over time, the internet has changed a lot. The internet has become a means for all sorts of interpersonal communications, right? So the types of files, or maybe more broadly, the types of content that we share has changed. And that's been driven by how people use the internet, right? And so I'm talking about delivering content in generally, just because we don't always think of certain things as being file transfers, right? The YouTube video that we were watching at the beginning of this, we don't really think about that as downloading a file from Google servers, although there is a sense in which it is, all right? So how does this work, right? How does this happen on the internet? Well, there are a couple of different ways. And certainly, you already know one of them, right? You already know about a client server model. So in this model, your server has the file. Clients send requests to the server for that file. The server receives the requests and sends the file back, right? So there are protocols that let you do this. FTP is one, stands for File Transfer Protocol. Even HTTP. That's essentially what HTTP is doing. And again, we tend to think about HTTP as, it's part of a URL, right? It's the protocol that dictates how we get content on the web. But that's what a website is, right? You are downloading that data from some server, right? So this is certainly one way to get content from a server to you. It has some drawbacks though, right? One of the drawbacks certainly is, it's a single point of failure, right? If this server goes down, where do we get the content from, right? Imagine we're back in the world of Katrina's Amazing Web Suite. If Katrina's Amazing Web Suite is only hosted on a single server and the server goes down, how are people going to buy llamas, right? It's a valid question. And so, some websites will start to say like, okay, well, instead of having, say, just one server, maybe I have like 2 or 3, right? And maybe I just use them as backup servers, or maybe clients can go to one of the 3 servers, right? There are ways to start to deal with this problem, right? They're not automatic things. And in fact, this is one of the places that we're going to focus on starting next week, right? How would we get such a system to work? But if we're thinking in the world of like, a small business or one person, having this kind of client server model, they're only going to run, maybe 1, 2, maybe 3 servers. This isn't going to scale particularly well. If our site gets really popular, right? If Katrina's Amazing Web Suite really takes off, and like, how could it not, right? We're not going to have enough resources in the network to handle all of the requests, right? We may also run out of compute resources, but we're going to be overwhelmed, right? All of these clients sending requests to our servers, the queues in front of my servers are filling up. It's just not going to work. All right. So let's think, how can we deal with that? All right. Well, one way to think about that would be to say, well, okay, if you keep adding servers, right? At some point, it's going to get difficult, maybe for me, a single person, to manage all those servers. Also, real talk, I hate managing servers, like me personally, so I would never want to have to do this. But we could start to use a resource known as a content delivery network, or a CDN. So that's what CDN stands for here, content delivery network. All right. So in a CDN, a single company would own all of these servers, and they would come up with a way to automatically redirect clients to sort of the right servers, right? A server that has the content they want, a server that is, maybe in the example I gave, lightly loaded, right? This is what a CDN does. We're going to talk a lot more about CDNs today, right? In fact, we're going to focus like almost half of the remaining part of lecture on CDNs. But before we answer all of those questions, like before I go into the details of this, I want to sort of just take this argument out as far as it will go, right? Because what we're starting to do here in this picture, we've moved from having the content on one server to have the content on, I have given you 3 servers in the picture, but maybe you imagine like thousands would be a better model. I just couldn't draw it on the slide. All right, let's take it all the way up. Let's put the content almost everywhere. All right, let's distribute this architecture kind of to the max. All right, and this is what is known as in some ways, as a peer-to-peer network, right? So P2P, peer-to-peer. And it can allow for some kind of organic growth. So I will give you, we're gonna talk about peer-to-peer networks more as well, but I'll give you a quick drawing here. All right, I'll keep it on the top of the paper so you can see. All right, so you can imagine I've got a server here. It's got the content. All right, I've got some servers. They all have the content. All right, so you show up, you want to download this file, right? Whatever file we're hosting on these servers, like the website that sells llamas or whatever. All right, so client shows up. So here's you. You come along. That's fine. You make a request to one of these servers. Say, hey, I'm interested in this content. Can you please send it to me? All right, the server sends it back. All right, and maybe it's a big file, maybe it takes a while, but eventually you get the content. Right now, if you sort of hang out here in this system, if your machine stays online, right, well, other clients can start to show up, and maybe some of them go to servers, right? So maybe some of them go to servers for the file. They start to download it from these servers, but maybe some of them ask you. You have the file now, right? Why not send it to these new friends, right? Same here. Maybe people start to come in, right? So in some sense, what a peer-to-peer network is going to try to do is say, well, hey, there's a lot of people interested in downloading this file. How can I exploit that, right? As some of them start to download the file, Maybe I've downloaded the first half of the file. Well, hey, now Felipe could download that first half for me, and maybe he gets the second half somewhere else, right? This is what a peer-to-peer network is doing, right? And we're going to talk more about that. All right, but notice with these three kind of options here, we have these 3 points in the design space, right? And what we're seeing is that, they're getting more and more distributed, which brings up the question of, wow, shouldn't they be more scalable, right? We're going to try to answer that as we go through this lecture. All right, but so we've got these 3 ideas, and we've talked about the first one a lot. We're not going to talk very much about the client server model today. We've talked about it a bunch. We know that it's very simple, especially in comparison to the other 2, and that's great. The fact that it's simple is really, really good. But it's got the single point of failure. We don't like that very much. It's hard to scale, right? It's hard to scale. But what about these other 2? What can CDNs do for us? What can peer-to-peer networks do for us, right? As I explain this to you, because we're, again, I said this was a bridge between the networking part of 033 and the more distributed systems, fault tolerance kind of part of 033. I'm going to take a particular look about what the underlying network is doing here. All right, CDNs, peer-to-peer networks, they are things that come up in sort of the networking space of systems. And so I'm going to make a specific effort to bring back things that you've already learned about networking. And despite the order that I have them here on the slide, I'm going to talk about peer-to-peer networks first. The reason I like to do that first is I find it more intuitive to think about CDNs in contrast to peer-to-peer networks. All right, so I did these, 1, 2, 3. We're going to go kind of backwards, 3, 2, 1. All right, so I got them all here on the side for you. And I'll tell you something. At this point in the semester of 2021, it has now been more than a year since I had access to a chalkboard. And I really, really miss drawing diagrams. And sometimes I get tired of making animations. So I'm going to draw these. I'm going to draw these systems for you. I think it's going to be good. I planned the drawings, so it should be nice. All right. So how does a peer-to-peer network work? There are lots of different styles of peer-to-peer networks. A lot of the details that I'm going to talk about come up in the BitTorrent peer-to-peer network. Some of you might have used BitTorrent. Some of you might not have. It's fine either way. All right. BitTorrent is a popular protocol used for file sharing. And the reason I like to talk about BitTorrent, I think it illuminates problems that occur in all sorts of peer-to-peer networks. It's still a very popular peer-to-peer network. It's the one that I know the most about. So it's like it's a win on all 3 axes here. All right. Sort of the basics of this protocol. Let's suppose, so we're going to share, I'll move this in a second. So sharing, we're going to share a file. We will share ubuntu.iso, right? So this is like a Linux ISO, all right? How is this going to work? I'm going to divide this into two parts, all right? So part 1 is just getting started, right? So getting started, what does this look like? All right, so if we want to share this file, all right, so Ubuntu ISO, that would be like a large file that sort of contains the Ubuntu operating system. Right. So the first thing that one would need to do to share this is to create a special type of file. In addition to just having the ISO somewhere on some server, we're going to make a specific type of file. And it's called a .torrent file. It's a relatively small file because all it contains is some meta information about the thing that you're interested in downloading. So it would include things like the file name, right? Like ubuntu.iso, the file size. It would include some information about, I'm just going to go ahead and use the word blocks, right? Because what we're going to find to make this network work, we're going to have this big file. So think of this as being like a, couple hundred megabytes and even a gigabyte file. It's going to get broken down into smaller pieces, right? And I'm going to talk about those pieces. I'm just going to use the word blocks. All right, so it has some information about these blocks, how large they are, hashes of the blocks, all of this kind of meta information. All right, so a client shows up. This is our client. When the client is interested in downloading this file, they have the torrent file. All right, so they have to have this file in order to get started. And so the first question you have as a new client who's trying to download a file as part of BitTorrent is just like, well, who else has the file, right? Where do I go to get it, right? Another way to say that in the language of BitTorrent is who's a part of the swarm, right? So here's how this works. One additional thing that is contained in this torrent file, and this is for kind of an introductory version of BitTorrent. So if you're a BitTorrent expert, just give me like 10 minutes. It's gonna contain the address of a server known as the tracker. All right, so have this tracker. Here's our tracker over here. Now the tracker isn't hosting the file, all right, but our client is going to go ahead and contact the tracker. And what the tracker is going to be able to send back to the client, right? So the client makes a request, and the tracker sends back IP addresses of people on the swarm, all right? So these are other clients, other BitTorrent clients that are downloading this file, all right? You know, maybe it sends you the entire swarm, maybe it sends you like 50 random people in the swarm. There's a lot of different options. But at this point, our client has the IP addresses of a bunch of people who are actively downloading this file. So what it can do now, it can go contact them, all right? It's going to speak BitTorrent to these clients, but it can go and say, okay, I'll contact this client and this client, right? It can contact all of these different clients. All right, so this is what we need to get started, right? We need this torrent file, which has, again, some meta information about what we're trying to download. And this torrent file helps us find other people that are actively downloading this file. So now we've found them, all right? What happens next? So that's gonna be, I'll move this over for you all in a second. Right, that is going to be part 2. Okay, 2, downloading. All right, so we'll even leave this little friend over here. All right, so after contacting a bunch of members of the swarm, here again, here's our client. This is you. Imagine that this is you. All right, embody this little picture here. All right, you've contacted a number of clients, a number of other BitTorrent clients. And, you know, we're going to assume that this set of clients that I've drawn here, they're all alive, all right? Their machines haven't crashed. They are actively downloading the file, right? And in fact, they're even sending parts of the file to you, right? So these clients, these are particularly nice. These are what we call your neighbors, right? So I'm going to color them in just so they sort of stand out here. I brought fancy markers for today's lecture. All right, so these are your neighbors. Right now, these clients, or we'll start to call them peers as they're in the swarm. It's a peer-to-peer network. These are peers. They have peers of their own, right? They've got other BitTorrent clients that they're talking to that, you know, you just maybe didn't discover from the tracker or didn't want to connect to you or whatever, right? Some of them might be talking to each other, right? There's a whole swarm out here. You're connected to part of it, but perhaps not all of it, right? And, you know, some of these entities involved in the swarm are special, right? We're gonna indicate that by this little symbol, right? So we'll call this a seeder. So a seeder is just a client that already has the entire file. They don't actually need to download any more of it from anyone else, but they have the entire file. They're kind of just sticking around. They're sticking around to seed the file. Right? So there could be a couple seeders. And you know, maybe you're a seeder because you're a server run by the Ubuntu Corporation, right? And you want to make sure there's always someone out there that has the file. Or maybe you're just an altruistic person, right? Maybe you're just hanging out. You just love being a part of this network. All right. So this is sort of how we picture BitTorrent, or we picture a peer-to-peer network, right? I'm downloading blocks, pieces of this file from some people. They're downloading from other people, right? This is what's going on, right? This description so far, though, it rests on everybody in this network being a really kind and generous person, right? In particular, the way that this is going is I have this file, right? It's broken up into a bunch of smallish pieces, right? You can imagine those pieces are about like 16 kilobytes, right? So they're quite small. I'm requesting pieces that I don't have. I'm kind of requesting them at random, like, hey, I need piece 6, do you have that? Can you send it to me? I need piece, 74. Can you send that to me? All of these requests are going around, and people are sending me blocks back, right? They're sending me pieces of these files back. So what would motivate them to do that, right? In particular, you are imagining that these peers here, they're all people like you and me, right? They're people in their home networks. We pay for internet. Like me uploading a bunch of data to other people, it's not a free operation, right? So what incentivizes everybody in this protocol to behave? What is stopping me from just coming in and saying, I'm not going to upload pieces of the file to anybody. I'm just going to hang out and let people send blocks to me, right? What prevents me from doing that? Right. So in BitTorrent builds in an incentive structure to its protocol. All right. So it has some incentives here. So here is how BitTorrent works at a very, very high level. Right. And there are a couple of different ways to tweak this, but again, here's you, right? You're this client in the middle. And we think about BitTorrent as proceeding in rounds. Imagine that a round is like 10 seconds, right? You could change that, but like 10 seconds is a good mental model. So what I'm going to do here is I'm going to look at all of the peers that sent me blocks in the past 10 seconds. And then I'm going to say, okay, who did I get the most blocks from, right? Maybe I got the most blocks from this neighbor. And, I'll actually count like the top 4, say. Maybe it was this neighbor, maybe it was these 4, right? And that could happen in a number of ways, right? This one gives me like 20 blocks. This was, 15, 13, and 12. And then these 2 only gave me like 3 blocks each. All right. In the next round, these 4 neighbors are going to be the ones that I send data back to. All right. So those are the ones that I'm willing to upload to in the next one. They gave me a lot of blocks in the previous round. I'm going to send blocks to them in future rounds, right? So it has this kind of built-in incentive structure. Now you could do different things, right? I did top 4, you could do top 3, or you could do top 6, right? You could change those parameters around. There's nothing special about 4, right? Other options, instead of doing, say, like just a top 4, like a strict cutoff, you could say, well, I'm going to kind of share everything proportionally, right? I'm going to give a lot of blocks back to these peers in the next round, but I'll give a few to these 2. You could do something like that, all right? But let's think about why that actually incentivizes people. If I show up and I never give blocks out to anybody, right? I'm trying to leech, is a word. So never give blocks out to anybody. I'm not going to end up in anybody's top 4, like anywhere in this network, right? No one's going to be sending things to me, right? So that is sort of how these incentives work here. It does bring up the problem of just, well, how do I get started, right? I show up in this swarm. I don't have any part of the file. I have nothing to offer anybody, right? Am I just doomed, right? Peers in these networks, they reserve a little bit of bandwidth to give away freely, right? So eventually I'll accumulate a couple blocks and then I'll start sharing them around. And, again, if I'm requesting them at random, right, there's a good chance that I'm going to have some blocks that one of my neighbors doesn't, and we'll be able to kind of do this mutual exchange, right? So again, very, very high level explanation, right? Let me tell you kind of what's important here. To make this happen, we had to, we took our original file, we had to organize it in a particular way, right? We wanted to break it up into pieces. We want our users to kind of request those pieces in a particular way, right? I did them at random. BitTorrent does something a little bit more sophisticated, but we wouldn't just want people requesting the blocks in order, right? Like block 1, then 2, then 3, then 4, then 5, right? That's not going to give us kind of the nice distribution that we want, right? This lets us put peers to work as soon as they show up. And then, of course, we had to think about how do we incentivize users to actually behave, right? And that is a big part of networking that we don't get to touch on very much in 033. But how do we make sure people adhere to this protocol? Right? That is a real thing. So there's still two interesting things to talk about here, right? One is failures, and where is the network in all of this, right? Like what is interesting here from a networking standpoint, right? So failures, we're gonna do failures first because there's one glaring failure issue, which is actually not on this side. It's this tracker, right? We use this tracker to get everything started. If the tracker were to go down, no one would know sort of who had the file. Nobody knows where the swarm is, right? Most modern BitTorrent clients today are what are known as trackerless BitTorrent clients. They operate using a really cool data structure known as a distributed hash table, right, or DHT, which have applications in a lot of areas of systems. But basically, it sort of distributes this information among a lot of people. And the torrent file gives you enough information to kind of get started with that. We are not going to talk about distributed hash tables in 6033 this year. It's a little bit outside the scope. But if you were like a theory person, that's a really nice bridge between theory and systems, right? Is one of the things that kind of got me, formerly a theory person, excited in systems. But beyond this is quite a resilient architecture. If one of these peers fails, right, leaves the network, not a big deal. There's so many others, right? Unless this was like, if there's no seeders and this peer was the only peer that had a particular block of the file, we're really good to go. If messages get dropped by the network, not really a big deal, right? So where is the network in all of this? Right? Yeah, of course, we're using the network to get messages between clients, right? But that's not a super interesting thing, right? The reason the network matters in this architecture, I started you off with this lecture with the question of, hey, these different architectures, they get more and more distributed. So shouldn't they get more and more scalable? In reality, peer-to-peer networks face some serious limitations, right? One of the biggest limitations of a network like this is that the kind of total capacity of this system is limited by how much these peers can upload, right? Like this client cannot download blocks any faster than this neighbor can upload them, right? That the connection is going to be limited by uploads. And I have bad news for you all as consumers who are paying for internet. Your download capability is almost certainly vastly superior to your upload speeds. Like when you buy internet from whatever ISP, it's, you might see an upload speed of like a tenth of what you're able to download, right? This is going to be a particular challenge if we're thinking about how to try to adapt peer-to-peer networks to like any sort of live streaming, right? Where then, kind of the what we can do is really limited by our upload capacity. We'd have some other adjustments to make in that case, right? Streams are tricky. They're not a file that you have beforehand and you can break into nice blocks, but we could probably get around that. It's really the capacity of this system, right? And one thing I'll note, you might not have thought about this before because the way we use the internet today, you're mostly downloading, right? Like I'm watching Netflix. I am not a Netflix server serving content. Right now, for my house, I am uploading quite a bit of data to you, but most of the time you're downloading a lot. And as Marcus put in the chat, it's an issue of economy and of the market. It's not technical, right? Comcast could give you more upload speed if they wanted, right? So here is, we'll bring back some pictures in a second. Kind of a summary of peer-to-peer networks, right? Requires us to do some particular kind of organizations of the file. We have to be able to discover our peers through something like a tracker, right? We need some incentives. And in practice, scalability here is limited by how the internet really works, right? This is sort of how we get back to CDNs. This is why I like to talk about peer-to-peer networks first and then CDNs, right? Because a CDN for us is going to address some of these limitations. All right, so bring back my paper and I will draw for you a CDN. All right, so CDNs are, in general, run by a single company. That company controls the servers involved, right? Their customers are people who own the content and want that content to be delivered to clients, right? People like you and me. So customers are paying CDNs for good performance. We should hope that a CDN performs well, right? There are many different content distribution networks. I'm going to talk specifically about Akamai, which is a popular content distribution network. Also, in Cambridge, it is right down the street from MIT. I almost said it's right down the street from us, but it's not, because I'm not on campus right now. So it's very close to home. You can walk by it and see all of the screens, which is cool. All right, so what does Akamai look like? In this picture on the left, I've drawn 3 servers. I need you to expand your mind much further than 3 servers. I need you to expand your mind to realistically more servers than I could possibly draw on this piece of paper. All right, you should be thinking like in the thousands of servers, right? Maybe even tens of thousands, but thousands of servers. I will draw this many servers. All right, so here we have a lot of Akamai servers, right? Where are they? What are they doing? These servers, right, are all across the world, right? So servers worldwide, right? So this isn't just a collection of servers in Cambridge. It's not even just a collection of servers in Massachusetts. They are everywhere, right? And the goal here is to replicate content across some subset of these servers. So let's say I'll draw this server as a special triangle. Right, so this is, we'll call this our origin server. And it's a server that sort of has the content to begin with, whatever content we want. All right, Akamai's job is to say, okay, I'm going to get this content onto some of my servers. All right, so we'll say, you know, maybe like these servers. All right, so all these Akamai servers, they form an overlay network like you've seen. All right, their network would have a lot more structure than what I am drawing for you here, but that's okay. We're just going for like a high level idea of how this system works. Let there be some more connections, right? So we've gotten this content to different places, all right? And then the goal is, if a client shows up, we'll draw 2 clients. So there's one client over there. We'll put another client over here, right? Without Akamai, both of these clients would make a request to this origin server and they would get the content back, right? But remember, this picture, despite what it looks like, encompasses the entire world, right? These clients are on opposite sides of the globe, right? What Akamai is going to try to do is, serve them content from somewhere that might be more useful, right? Perhaps the server closest to them. We'll start with that, right? The server closest to them that has the content. Right now, there is a lot that goes on in a system like this. Right, Akamai is going to be super smart about replicating content. Right, kind of only putting it in places that it needs to be replicated. It's going to be very smart about caching things, all of these sorts of things. It brings up a lot of questions. Right, where should these servers be? Like geographically, where should we put them? Doesn't matter. Right, how do we actually get the content to these servers? How do we get that content up to date, right? Imagine that our original content is like a dynamic web page or something like that, something that changes frequently. And how do we get clients to the right server, right? The right server would be one that has the content that they're looking for and is going to provide good performance, right? For whatever that means. And all of this should work kind of behind the scenes. Clients shouldn't know about this. I can guarantee you that all of you have looked at content online that is hosted by Akamai, right? And I would also imagine that many of you did not know what Akamai was before this lecture, which is fine. Why would you have, right? Now, some of these questions, for instance, how we would keep data consistent across all of these servers, those are the type of thing that we're going to start to think about next week, right? So what I'm going to focus on right now is, how do we get users to the right place? How do we get clients to the right place? And where do we put these servers? And like, where is the network in all of this? How is the underlying structure of the internet affecting this architecture? All right. So getting users to the right server. Here's a concrete example for you. This website, which I would bet all of you have visited at least once, right? web.mit.edu. The content on this website is hosted by Akamai, right? And yet you have probably visited this website without knowing anything about Akamai, right? The way this works is that Akamai uses DNS to get you to the right place. So we are bringing back DNS. It is lecture 2 all over again, all right? If you, for instance, we can do it together if we want. We'll hope that this demo that I didn't plan works. You could run something like this. I'll show it to you in a second, right? You could run dig on web.mit.edu, right? And you'll see a couple of interesting things. You'll see that web.mit.edu is actually a canonical name for this weird looking thing, right? www.mit.edu.edgekey.net, right? So edgekey, that's an Akamai thing. That's the phrase they've gone with. And that redirects to this other particular Akamai server. And then that gets you down to an actual IP address. And I would bet that some of you, especially if you are running this in different parts of the country, are probably getting something that looks different, right? You're probably getting down to a different physical IP address, right? Akamai has actually made it legitimately challenging for me to come up with DNS examples in class because so much is hosted by Akamai. All right. So this is how we get clients to the right place. This client, your browser makes a DNS request, right? And it gets directed to one of these physical servers, right? So this client over here, the DNS request ended up at this IP address. And then this client over here, same website, right? Ends up over here, right? So now, gosh, how does Akamai decide? There were lots of different options, like 4 in this diagram, but in general, lots of different options. Oh, 5, I guess, right? How does it decide, right? Well, some of that is going to be proprietary, right? So that is part of what you are paying Akamai for, to do a good job at this problem. But one of the things that they care about very much, like for sure, Akamai publishes lots of things, so you can learn a lot about this. They do care very much about latency. They care about getting clients connected to a server that is close to them, right? And they infer that from sort of the IP address from your original DNS request. They can make a assumption about where you are in the world, right? They care a lot about latency. Specifically, they care a lot about how latency affects TCP. And I think that this is a very interesting issue because a lot of times we can get kind of focused on throughput, right? We usually think, oh, we're streaming videos, like we're trying to download a bunch of content real fast. Like, how much does it matter how long that sort of first bit takes to get to me? But now you know enough about TCP that we can have this conversation, right? Latency and throughput are very much coupled, right? So for instance, in TCP, you're only allowed to send a window's worth of data at a time, right? Before you sort of, pause and wait for acknowledgements to come back on the receiving end. Right. Now, if TCP is doing a good job, things will be paced more evenly, but you still have this notion of that round trip time making a big difference, right, in how your window increases and how long you have to wait before you can send more data. This can become a bottleneck for like download speeds, for file download speeds or for video streaming, things like that. So to deal with this further, so Akamai is getting you to the closest server in part because they care so much about latency, but they also care about latency within their own network. And they do two things that are super relevant to what you have already learned in 033, right? One of the things that they do between their servers, so in their overlay network, they tend to keep persistent connections open between these servers, right? So they've created this overlay network. What this means, like concretely in terms of TCP, they're not in slow start over and over and over. They have sort of stable TCP connections. They've got their windows set to, roughly the correct size. Obviously it changes, but they're out of slow start. They don't have to worry about that, right? And when they describe all of these optimizations, I'll put online some of the papers that Akamai has published, just in case you're curious, not required reading by any means. They talk about how a lot of the applications they do here require them to own both endpoints. All right. They need to own the sender and the receiver, which they do in this overlay network. But that's a particularly interesting for you to think about in the context of the paper that you're going to read tomorrow for recitation. Akamai also kind of rolls their own semi-reliable transport protocol for some of these connections. They build it on top of UDP, not TCP, so that they don't have the overhead of TCP. So one interesting thing, they do some clever things at the transport layer. Second interesting thing, because they have all of these servers, because they put them worldwide, they're putting them in multiple different autonomous systems, multiple different ISPs, right? That matters here because since they have these persistent connections, they're able to find routes that BGP might not, very much like what RON does, right? And Akamai will claim that this can speed up communications between these servers by like up to 50%, which is, quite a lot if it's true. And that is particularly useful when Akamai is dealing with content that changes a lot, right? So content that can't easily be just cached in this network, content that they have to kind of keep retrieving from origin, these like origin servers, right? Again, maybe it's a video stream, maybe it's dynamic web content that is personalized for you, right? And so they'll even say in some of their literature that this type of optimization depends on the availability of this vast overlay network that includes machines in many different networks, many different ASs, many different ISPs worldwide, right? So this is the basics. And like I said, there are a lot of different content delivery networks. Akamai is used for a lot of traffic. Some interesting things, some companies, if they get big enough, will actually build their own CDNs. So interestingly, Netflix has, or I at least did the last time I checked, has its own CDN. So Netflix is not a customer of Akamai. It has built its own because it wants to tailor the experience specifically for the type of content that it serves, right? So CDNs, pretty interesting technology. I think the way they work is super interesting. They require a lot of coordination and organization among these servers, which they will often call edge servers, right? So that's what, does Netflix live on Amazon now, Howie? I'm surprised. We'll Google. All right. It's not as organic as a peer-to-peer network, but it can provide better performance guarantees, right? In part because it has this huge, this huge overlay network of its servers. It can find alternate routes, can improve transport layer performance, and also, again, you're paying Akamai for this service. You're not paying anyone in a peer-to-peer network, right? So you had better get some performance guarantees, right? I'll just kind of recall that in contrast to what we ended up with for peer-to-peer networks. And to complete this diagram, I do want to point out, although the client server model doesn't scale well, it's a lot less complicated than CDNs, right? So I've gone through these technologies. What are you meant to do with this, right? How does this relate to other stuff in 033? What do you take away from this, right? So there's kind of, in my mind, there's like 2 or 3 big things to take away here. So one, the way we share content on the internet has changed, right? Because the way we use the internet has changed. These days, notice that, we don't really just want content eventually. I want it on a particular time scale. Like when I was growing up, and maybe we would download music, maybe it was legal, maybe it wasn't, who can say? You would like, on your dial-up connection, you'd set it to download and you'd be like, I'll just come back tomorrow morning and see if this is finished, right? Like I didn't need it right now. Now I want Spotify to play me a song right this second. I want it to come to me quickly. I don't want to wait, right? You can also think about peer-to-peer networks and CDNs as ways of, in some ways overcoming or just adapting to the changing needs of humans and the original architect of the internet. Sometimes in 033, we'll talk about using peer-to-peer networks, to get around particular parts of the internet. In the early days of Skype used to use a peer-to-peer network to deal with some limitations of NATs, right? So these networks have other applications. We're not going to talk about that one this year, so you don't need to know anything about that. But then also, these different architectures are affected by the underlying network, right? And it's not just because we need to be able to send data between machines. Like, yes, of course, we need a network to do that, right? But we saw peer-to-peer networks can be limited by users' upload bandwidth. CDNs do, some very smart things at the transport layer, some smart things with routing. They also bring up interesting problems in the realm of failures, which is what we're headed into starting next week. In fact, if you read any of the design documents about Akamai CDN, it is explicitly designed for failures. Like, the fundamental design assumption that they rest on is essentially that everything is failing all of the time, right? We haven't touched on these issues yet. We haven't talked about how a company like Akamai would keep data consistent across servers. We haven't talked about how it would deal with a server that goes down, right? How would it detect that? How would it make sure to route clients away from that? And then what to do if it comes back up, right? Is it good to go right away? Does it need to do some sort of recovery process? Could it recover into any sort of inconsistent state? All right, all of those are problems that we'll start considering next week. All right, but now you know everything about networks, right? So if I hope that in the past couple of lectures you've seen a couple of different things, namely this slide, right? So we have talked about different protocols that exist at all of these different layers, right? Remember, one of the nice things about a layered model on a network is that you can swap different protocols out, right? I can pick different routing protocols. I can pick different link layer protocols. I don't have to run everything over Ethernet. I can use Wi-Fi, I can use Bluetooth. I have all these options, right? We've talked about the transport layer. We have reliability. We don't always want reliability, right? And now today, you've kind of seen how what's going on in the network has a big effect on how we build applications, all right? And then, as much as we, a lot of the things we've talked about, these are all problems that come within any network, data center networks, local area networks, all sorts of things. You've seen some specific things related to the internet, right? A lot of, you've seen that, okay, the scale is incredible. The internet is so big, like, it's really big. That's, if you take one fact away from 033, the internet is really big, all right? So we have to deal with scale. We also have to deal with diverse groups of, or diverse types of applications, right? Some things care about latency, some things care about throughput, some things are, some things have a lot of data to send, some things don't have a lot of data. Like, there's all of these different types of needs, right? The fact that the internet works for all sorts of different applications is quite frankly phenomenal. That is amazing, right? And you've also seen how humans matter here, right? The way that we, as just humans, not even people interested in computer science or systems, like just humans, the way we use the internet has changed what the internet can do, right? CDNs didn't always exist, right? They didn't always exist in the same way that they do right now, right? Peer-to-peer networks didn't always exist. We weren't streaming Netflix in the 70s, right? And then you've also seen, humans use the internet. Humans also pay for the internet, right? And that brings up its own set of challenges. All right. So that's kind of the summary of where we've, where you've been in terms of networking, what you're getting ready for, all right? What you're getting ready for at the end of next week. We've focused on operating systems, right? So you have a sense of how a single machine works. You now have a sense of what the network between machines can provide, right? What we're going to start talking about on Wednesday, because remember, no lecture Monday, we're going to start talking about on Wednesday, how do we build resiliency and reliability into these large distributed systems now? Because we're ready. You've got operating systems, you've got networking, you're ready to build things like a CDN, right? So what's going to happen when servers fail? What's going to happen when you can't store all of your data on a single machine? How are we going to deal with that, right? Those are the things we're going to start talking about on Wednesday. Yeah, I'll see you then. Watch out on Piazza again for a post about the exam. I'm intending to post it right now. So let's say it's going to happen in the next hour or so. So let me stop sharing, stop recording.